Hello students, welcome to my lecture series on reinforced concrete structures. In this class, I am going to discuss about a complete design of two-way unrestrained slabs based on limit state method as per provisions of IS 456-2000. So let's see what are the outcomes of today's class. Upon completion of this class, the student will be able to design by its own a two-way unrestrained slabs. Then that is a let's see the steps what you follow for design of two-way and distance slabs. First, we have to calculate what is the effective depth is. This effective depth of the slab consider based on the stiffness criteria of IS 456-2000, that is L by D ratio we have to choose as per IS 456-2000. So the condition for this choosing Lx by D ratio is if Lx means a length of shutter span direction is less than 3.5 meters and a live load is less than 3 kilonewton per meters, then if you are designing a simply supported two-way slab and you are using a grade of steel is say Fe 415, then that Lx by D ratio will be taken as 28. If the case is reverse, say Lx is greater than 3.5 meters and live load is greater than 3 kilonewton per meter square, then we have to assume our Lx by D ratio same as that of one-way slabs. Say in one-way slab, we have assumed Lx by D ratio as from 25 to 30. Between those two values, we can choose what are the Lx by D ratio value and we have to calculate what is the effective depth is. So this is how we calculate, we will assume the effective depth based on the stiffness criteria given by IS 456-2000. Next, we have to calculate effective span here. As we are designing a simply supported slab, say the effective span will be considered as a minimum of those two criteria. The first criteria is clear span plus effective depth. Second criteria is center to center distance between the supports. Okay, so these two criteria first we have to calculate. That is clear span plus effective depth, and second center to center distance between the supports. Among those, minimum value will be considered as a effective length in particular direction. Same, we can calculate effective span in Lx direction and effective span in Ly direction also, right? Then we have to calculate loads. Loads we have to calculate. Generally, we have 3 or 4 types of load. Generally, we can say 3 types of load. That is dead load, that is sulfate, live load, floor finishes, total loads. The total load nothing but sum of all three loads, that is dead load plus live load plus floor finishes. And after obtaining this total load W, we have to multiply this with the partial factor of safety, that is 1.5. So then we'll get the factored load W is equal to 1.5 into total load. So total load, after calculating total load, we go for calculation of bending moment calculations. As we are designing a two-way slabs, the bending moment will be calculated along x direction, y direction, because in two-way slabs our bending moment occurs in both the direction, x and shorter direction, longer direction. That's why we need to calculate mx and my. Here mx is the design moment along the shorter span, my is the design moment along the longer span, and here we have alpha x and alpha y. These are the bending moment coefficients. They will depend upon the edge condition of the slab, and w is the total design load on the slab. Lx is a shorter span, that is effective shorter span. By knowing these terms, if you substitute the values of all those terms in this equation, we will get what is the mx value is. Mx equal to what? Alpha x w lx square. Mi equal to alpha y w lx square. From this we can calculate, right? Then here, as we are designing a unrestrained slab, so the bending moment values, coefficient of bending moment can be calculated by using table number 27 of IS 456. So those values are depends upon again Ly by Lx value. If the Ly by Lx value is given like this 1, 1.1, 1.2, 1.3 and so on, and their corresponding alpha x and alpha y, that bending moment coefficients are like this. From this table we can calculate our what are our alpha x and alpha y values are. So after knowing that, if we substitute the alpha x and alpha y values here, we'll calculate mx and my. So after calculating maximum bending moments along the x direction, y direction, we have to go for check for effective depth. So that is check for minimum effective depth required. So for application of maximum bending moment, what will be the minimum effective depth required for the particular slab, that we have to check. That means whether our assumed depth, effective depth in our initial step, first step is whether sufficient or not, that value we have to check here. So for checking the effective depth, here we have to equate the maximum bending moment to the limiting moment of resistance of the section. So mu is your maximum bending moment, mu limit is the limiting moment of resistance. Mu means what? Mu value will be considered here maximum of a bending moment values along the x direction and y direction. Suppose we are getting maximum value in x direction, here the bending moment value corresponding x direction will be substituted. Suppose we are getting a bending moment value maximum in y direction, then you have to substitute here bending moment value corresponding to the y direction in place of mu and calculate the what is the minimum depth required. Say the minimum depth required can be calculated by formula d equal to under root of mu by k into fck into b. Here k is the grade of concrete and b is the 1 meter width of the slab we are considering, and this k value depends upon what grade of steel we are using. So generally we will use Fe250, Fe415 and Fe500, and corresponding K values are given here. So for Fe250 it is 0.148, for Fe415 it is 0.138, and for Fe500 it is 0.133. So value should be obtained from this, that is the minimum effective depth required is less than or equal to the depth assumed in our first step, then our design is okay, we can go for further steps. And if the required depth is greater than the depth assumed, then we have to revise this depth and then we go for the remaining steps for designing. Okay, this is how we calculate effective. We have to check our minimum effective depth with our assumed depth. Then we go for a calculation area of steel. So as you know that area of steel can be calculated in three regions, that is mid-span, left edge direction and right edge span direction. So in both ways we have to calculate. So our slab is divided into middle strips and edge strips along the x direction, y direction. In those regions we have to calculate what are the area of reinforcement to be provided. So the area of reinforcement in mid-span region, means middle strip region, in x direction and y direction will be calculated by using these formulas. So in x direction we can calculate mux is nothing but a maximum bending moment along the x direction is equal to 0.87 Fy ASTX into D a whole 1 minus Fy ASTX by FCK into BD. Here B is the 1 meter width of the slab, D is the effective depth of the slab, Fy the yield strength of steel, and D is the effective depth of the slab, you know. So if you substitute all those things in this equation, and this MUX is already we have calculated when you are by using the step called calculation of bending moments with respect to x direction, that value you have to substitute here, and after substituting values and calculating that, we will get a quadratic equation. If you solve that quadratic equation, we will get what is the ASTX is. And similarly we can calculate ASTY. ASTY means area of steel provided in a middle strip region along the y direction. So that can be calculated by using this formula. MUY is equal to 0.87 Fy ASTY D dash into 1 minus Fy ASTY by FCK to BD. So please correct this formula. This 1 will not be here. This is 1 minus of this total value. 1 minus of Fy ASTX by FCK into BD. Right? Some mistake here. So substitute the values of Fy ASTY and D dash in this equation. We will get what is the value of ASTY is. Right? Here also we will get a quadratic equation. After solving that, we will get ASTY is. So this is how we calculate area of steel in middle strip region along the x direction and y direction. So after calculating area, we have to provide that area into number of bars by providing some spacing. So that can be calculated. You know how to calculate D and D dash. D is the effective depth and D dash is the overall effective depth in y direction. So by using these formulas we can calculate, and reinforcement is provided as follows. Now how the reinforcement is provided x as well as in y direction. First you have to place our main reinforcement along the shorter direction. Then over the shorter direction reinforcement we have to place our y direction or a longer direction reinforcement, because in shorter direction we have a capability of resisting more movements. That's why we are providing shorter direction reinforcement bottom, and over that we are providing a longer direction reinforcement on the shorter direction reinforcement. So here, as for codal provisions, we have to maintain some spacing that for that main bars along x direction as well as in y direction. So that spacing of main steel bar should not be more than following these two. So 3D and 300 mm, whichever is less. But generally, we can calculate a spacing by our data, the given design data, and that spacing also consider the obtained value of spacing and is 3D and 300 mm, whichever will be the less, that value will be provided as a spacing for main reinforcement bar, that is along x direction and y direction. So that is all about your calculation of area of steel in middle strip region along the x direction, y direction in those cases. Now we have to calculate area of steel at edge strip along x direction and y direction, and code suggests that the area to be provided in this edge strip region is, that is, minimum area of reinforcement provided. So as for codal provisions, the minimum area of reinforcement provided for FE 415 bars, that you can say HYSD bars, is 12% of gross cross sectional area. And if you are using FE 250 bars, then we have to provide area of steel is 0.1% to 0.15% of gross cross sectional area. Right? That is depends upon a grade of steel what we are using. Based on that, you can calculate what is the minimum area of reinforcement provided in area of steel at edge strip. And here also we have to maintain some spacing. The spacing would be as per IS 456 2000, that is 5D and 450 mm, whichever is this. And here also we can calculate what is our actual spacing to mean. Based on the data, we have to calculate what the spacing to be provided, and then we have to check upon obtained value of spacing 5D and 450, whichever is the less, those value will be provided as a spacing for this steel reinforcement provided in edge strip region. Right. Then we go for check against the deflection. The deflection for check will be done based on the two parameters like percentage of steel and stress in steel under service load. And percentage of steel, you know how to calculate, that is PT equal to 100 AST x by 100 AXT provided whole by area of cross section, that is B 1 meter width, and D is the effective depth of the slab. According to this, we can calculate what is the percentage of steel. Then we have to calculate stress in steel under the service load, that is Fs. But based on this formula, we can calculate this formula given in your IS 456 2000, that is Fs equal to 0.58 Fy into AST required by AST provided. Based on these two values, PT and Fs value, we can calculate modification factor. This is called a KT. This is useful to you for calculating L by D max. And that L by D max will be compared with our L by D provided. If the L by D max value is greater than L by D provided, then we can say our slab is safe against controlling the deflection. Then how to calculate this KT? So for particular percentage of reinforcement, that is on x-axis, and y-axis we have a modification factor, and in between we have some curves related to the Fs. And suppose if you are getting 0.8 is the percentage of steel, and you have what is the 240 is the Fs value, then 0.8 corresponding you have project onto the Fs curve, that is 240 corresponding 240, and after intersecting point of the 0.8 percentage of steel and curve, then the same thing horizontally you have projected onto the your y-axis. The value of whatever we get on y-axis, that will be your modification factor. Say here with respect to this, so this is 0.8 and this is 1.2. We are getting somewhere here, so it will get 1 and 1. I can say 1.05 or 1.1 here. So with respect to this, I can write the modification factor value will be 1.05. Like that, we can calculate modification factor and substitute here. Then I will calculate what is L by D max is. Right? And similarly, calculate L by D provided. L by D provided means Lx, that is the shorter span direction. D is the effective depth of the slab. Calculate the ratio of that. That ratio must be less than L by D maximum ratio. Then only we can say that our slab is safe against the deflection. Next, we have a check for shear. Generally, we will not do this for simply supported slabs, but anyhow, we'll see here. So, first for calculating the check for doing the check for shear, we have to calculate what is the shear force, factored shear force along the x direction. Say that factored shear force can be calculated by using this formula. So, W equal to W into R power 4 by 1 plus R power 4 whole multiplied by Lx by 2. Here R equal to Ly by Lx for simply supported slab. If you substitute the values of this, we will get what is the UX. Then we have to calculate nominal shear stress according to the code IS 456 2000 class number 40.1. So tau E can be calculated by VUX by BD. You know, already we have calculated VUX. B equal to 1 meter width of the slab and D equal to effective depth of the slab. If we substitute those values, we will get what is the tau E is. After calculating tau E, we have to calculate what is the design shear strength of the concrete. And this design shear strength of the concrete is depends upon grade of steel, grade of concrete and percentage of steel provided. So the percentage of steel is like on this table number 19 of IS 456 we can take here. After calculating percentage of steel, corresponding value of percentage of steel we can locate on the table number 19, and grade of steel, grade of concrete given is 20 and the percentage of steel provided 0.25. The corresponding value of tau C is 0.36 Newton per mm square. Like that we can calculate tau C value. But if this is with respect to slab, this tau C value can be calculated. That value should be obtained tau C value should be multiplied with a some factor called K. That K value will depend upon a overall depth of the slab. So this is the table given in the IS 456 2000 according to class number 40.2.1.1, and values are like this. 300 for 300 mm and more we have 275, that is 1.05, like that for the one, and so on. 150 or less we have 1.30 is the K value. So if you calculate multiplying the obtained tau C with the K, we will get some value. That value must be greater than our nominal shear stress. Then only you can say our slab is safe against the shear. Then we go for checking of development length. That is development, you know how to calculate development length and check the development length. LD equal to less than or equal to M1 by V plus L0 is L0 is the anchorage length, VU is the factorial shear force, M1 is the bending moment at section considered. And LD can be calculated by 0.87 Fy into 4 into tau BD. Here tau BD is the bond stress, Fy is the yield strength, bar is the diameter of bar used. So after calculating LD, calculated LD must be less than this factor, that is M1 by V plus L0. Then we can say our slab is check against the development or safe against the development length. Right? So with based on those steps, let us solve one design problem. Let us design a slab here. So what is the problem given to you? Design a RCC slab for a room of clear dimensions 4000 mm by 3000 mm. The slab is supported on walls of width 300 mm and the slab carrying a live load of 3 kN per meter square, and floor finishes is 1 kN per meter square. So use M20 concrete and Fe415 steel. The corners of slabs are not held down. So corners of the slab are not held down. So from this we can conclude that from the last sentence we have to design a unrestrained slab. You know what is the meaning of unrestrained slab is? The corners of slab are now free to lift up. So let me explain the problem again. We have to design a RCC slab for a particular room. The dimensions are 4000 mm by 3500 mm. So the 4000 mm is more than compared to your other dimensions. So that will be considered as a LY. So LY equal to 4000 mm. So we can write here, that is in terms of meters. So LY equal to 4 meters. And similarly, your LX, there is shorter dimension 3500 mm, that can be written as LX equal to 3.5 meters. Now in the problem it is not mentioned that what type of slab we have to design, whether we have to design a singly reinforced or doubly reinforced. That will be depend upon our LY by LX ratio. So let us check what is the LY by LX ratio is. So LY is say 4 and LX is 3.5. So it is a 4 by 3.5 will get somewhere now 1.14, which is less than 1. So we can design it as a two-way slab. Finally, we can design our slab a two-way slab, that is unrestrained slab. Well, with the data given is the clear span is 3.5 meters along the x direction and the clear span along the y direction is 4 meter. Live load is equal to 3 kN per meter square and floor finishes are equal to 1 kN per meter square. And the characteristic compressive strength of a concrete is 20 Newton per mm square. And finally, the yield strength of a steel is 415 Newton per mm square. So based on this given input data, we have to design our unrestrained two-way slab which is supported over a four edges, four support, simply support corners. First we have to check, assume the effective depth. So for this we have a one consideration that we have to check our LX value and live load value. If our live load is greater than 3.5, LX is greater than 3.5 meters and live load is greater than 3 kN per meter square, then we go for what? LX by D ratio is the same as what we consider for one way slab. So in the problem it is given that our dimension is 3.5, so and live load is 3. That is exactly equal to that. So you can take that or this. So I am taking for this, I am designing it as LX by D ratio is same as that of one way slab. For calculating the effective depth, assume the suitable depth based on the stiffness criteria consideration, that is LX by D ratio equal to 25 to 30, it will varies. So I will assume 28, the middle in between value, that is 28 as a basic value. From that I will calculate what is the effective depth is. So the effective depth equal to span per basic value. The basic value will be 28 here. So the span means it is a shorter directional span. So small d equal to 3500 by 28. We will get 125 mm is the effective depth. This is assumed depth, purely assumed based on the stiffness criteria of the slab. Okay. And based on this, we have to calculate what is the overall depth of the slab is. So adapt a clear cover 20 mm and use 8 mm bars. The total depth can be calculated by using this formula, that is effective depth plus clear cover plus diameter by 2. So effective depth is 125 mm, clear cover is 20 and the diameter of bar used is 8. So 8 by 2 will get 149 mm. Say use it as round figure, that is 150 mm is the overall depth of the slab. In second step, we have to calculate effective span of the slab based on the given data. Say effective span here, we have to calculate effective span along the x direction and along the y direction because we are designing a two-way slab. So for calculating effective span along the x direction, we have a two criteria, that is clear span plus effective depth of the slab. Clear span is 3500 mm in x direction and effective depth of the slab is 125, that is we are assumed here. So that is total equal to 3625 mm. The second criteria would be center to center distance between the support, and here that can be calculated center to center support equal to clear span plus half width of the one support and another half width of the another support. If half width of the two supports if we add, we'll get one full width. That's why I'm using here 3500 plus one full width of the slab is, one full width of the support is 300 mm. So if you calculate these two, we'll get 3800 mm. This is the effective span along the x direction according to the second consideration. Now we have calculated effective spans along the both consideration, but we have to choose minimum of these two values. The minimum would be what? 3625 mm. So hence effective span Lx can be provided, that is 3625 mm, that equal to 3.625 meters. Similarly, you can calculate the effective span along the y direction. The clear span plus effective depth of the slab, that is clear span is 4000 mm along the y direction and effective depth is 125, will get 4125 mm, and the second criteria is center to center distance between the support, that is 4000 plus 300, 4300 mm. So minimum of this two value is according to the criteria of A, so that is 4125 mm. So hence effective span along the y direction is, that is Ly 4125 mm. Now calculate the loads for considering 1 meter square area, as our loads are given in meter square something, and the self weight of the slab is D into unit weight of the RCC. So we have that self weight, what is this overall depth? Sorry, this is 150, 10, not 108 is there. Please correct it, this is 150, 0.150 multiplied by 25 will get 3.75 kilonewton per meter square, and live load equal to 3 kilonewton per meter square, and finishes are 1 kilonewton per meter square. Then if we add all together, the total load would be dead load plus live load for finishes. Dead load equal to 3.75, live load equal to 3, and finishes equal to 1. If we add all together, we will get total load would be 7.75 kilonewton per meter square. Then you have to multiply the total load with 1.5, we will get a factor load. 1.5 to 7.75 kilonewton per meter square, we get 11.625 kilonewton per meter square. So this is how we calculate factoral load. After knowing the factoral load, since the slab are supported on all four sides, its corners are not held down. That means it is free to lift. Then the bending moment coefficients are calculated as per IS 456-2000 table number 27. That factors are depends upon, the coefficients are depends upon Ly by Lx ratio. The Ly by Lx ratio is like this, and alpha x values are like this, and alpha y values are like this. From this, by knowing that Ly by Lx ratio, we can calculate what is alpha x and alpha y. Let us see. So before that, Ly by Lx ratio is this 1.14, and alpha x alpha y value directly we are not having that value. The 1.14 means it is in between 1.1 and 1.2, so we are getting value somewhere here and here. So if you do the interpolation technique, we'll get alpha x equal to 0.078 and alpha y is equal to 0.06. Based on this, we have to calculate what is that bending moment values along the x direction, that is mx equal to alpha x w lx square. Alpha x equal to 0.078 into w is already we have calculated 11.625 into Lx is 3.625 square. If you multiply all those values, we will get the maximum bending moment along the x direction is 11.92 into 10 power 6 Newton into mm. Similarly, calculate the maximum bending moment value along the y direction by using the formula called alpha y w into Lx square. You know alpha y value is 0.06, w is 11.625 into Lx is 3.625 square. Then mi, the maximum bending moment along the y direction is 9.17 to 10 power 6 into Newton into mm. Then we have to calculate or check for effective depth, that is minimum effective depth required for that particular bending moment. So for this we have to equate maximum bending moment to the limiting moment of resistance. From this formula, the minimum effective depth required is under root of mu by k into fc k into b. We can calculate what the d is. So you know what is mu is? Mu is the maximum value of mx and my. So with respect to these two values, the maximum value will be corresponding to the mx. So mx value will be substituted as a mu here. So after substituting that 11.92 into 10 power 6 by 0.138 into 20 into 1000, we will get 60.7 mm. But our assumed depth is 125 mm. So our assumed depth is more than that minimum depth required. So no problem, we can go for further steps. Then we have to calculate area of main reinforcement along the shorter direction middle strip and longer direction middle strip. The shorter direction, shorter span, width of the middle strip will be 3 by 4th of Ly, that is 3.09 meters, and MUX equal to 0.87 Fy ASTX D into 1 minus Fy ASTX by FCK into BD. If you substitute the values, the MU equal to 11.92 into 10 power 6 is equal to 0.87, Fy equal to 415, ASTX here. Here I have to substitute ASTX, that is the area of steel in middle strip along the shorter direction, and effective depth we have is 125, and into 1 minus 415 ASTXY 20 into 1000 into 125. Here we get a quadratic equation. If we solve this quadratic equation, we can calculate what is the ASTX is. The ASTX equal to 276.8 mm square. And for this we have to calculate what the spacing to be maintained. So using 8 mm diameter bars, spacing for this is equal to small AST by capital ASTX into 1000. Small AST is area of 1 8 mm diameter bar, and that will be 50.3 mm square. So S equal to 50.3 by 220, I think it is 276.8 AST generally, 276.6. You will get the spacing is, after calculating that, we will get spacing is 181.6, and 3 times diameter is 375 and another is 300 mm. So among these three we have to provide whichever is the less. So less is 181.6, so we can round it to 180 mm. Hence provide 8 mm bars at 180 mm center to center distance. And along the y directional we also have to calculate the width of middle strip is 3/4 of Lx. 3/4 of Lx is 2.75 meters, and effective depth then calculated is d dash equal to d minus 5, that is 125 minus 8, that is 117 mm. Now substitute all those values, we will get the area of steel along the y direction is like this. AST equal to 226.2 mm square. Right, calculate the spacing for this 226 mm square. That is equal to small AST by capital AST y here generally 1000 and area of 18 mm diameter by 50.3 and is equal to 50.3 by 226.2 AST y equal to 1000. We'll get 222.2 and the spacing for as per IS 456 2000 provided is 351, that is corresponding to 3D at. Another is 300 mm. Minimum of these three, which is a lesser value, that will be provided as a spacing for the bars which are provided in a longer directional middle strip. So the value hence provide 8 mm diameter bar at 220 mm center to center. And coming to our area of edge strip, minimum area will be provided as we are using Fe415 steel. So 12% of gross cross-sectional area we have to provide. So 0.12 by 100 into 1000 into 150, that would be 180 square. And here also we have to maintain some spacing. We are using where 8 mm diameter bar. Spacing of that bar would be is equal to small AST by capital AST of 180. If you substitute here, we'll get small that spacing for according to our data is equal to 50.3 by 180 into 1000. We'll get 279.3 mm. But according to the code, the spacing to be maintained by 5D, that equal to 625. Another condition is 450 mm, whichever is less. But we have a 279, 265, 625 and 450. Minimum of these two values will be used. So hence provide 8 mm bars at 275 mm center to center. So this is all about design process. Then we go for check. For checking, first we have to check for the deflection. For checking the deflection, we require what are the parameters: percentage of steel and Fs, that is stress under steel in steel. We have to calculate percentage of steel can be calculated AST 100 AST x by BD. If you substitute that, we will get 0.233%. And stress in steel under the service load Fs can be calculated by using this formula. Fs equal to 0.5 Fi AST required by AST provided. Then we get Fs equal to 240 Newton for mm square. So after getting these two values, we can go for our graph which is provided in IS 456 2000. So corresponding 0.223 percentage of steel and 240 Fs, and what is the factor of modification factor is. So here the 0.4 is 0.2. So our value somewhere here, that is 0.223, will project onto our graph. You will say we are going somewhere here. So with this, I will intersecting here. The value will be intersecting here somewhere here. So this value intersecting here. So with respect to this, the modification factor approximately equal to 1.7. So according to modification factor, I can calculate what is L by D maximum is. So basic value for simply supported slab is 20 and the factor of the modification factor is 1.7. If we multiply it together, we will get 34. So what is the provided one? Provided means L by D provided is the L is Lx, L nothing but Lx 3125 mm by depth is effective depth is 125. So if you divide 3125 with 125, we'll get 25. So from these two values, we can say our L by D maximum is greater than L by D provided. Hence our slab is safe in deflection control. Next, we have to check for development length LD, that is M1 by VU plus L0, and here M1 can be calculated with respect to this formula, that is maximum moment of resistance 0.87 Fi ASTX into D minus 0.42 XU max. So moment of resistance we are calculating with respect to maximum depth of neutral axis, so I can call it the maximum moment of resistance. So M1 equals 0.87415, AXTX is 276.8, and small d is 125 minus 0.42 into 0.4. You know that XU max for the Fe415 is 0.48 times the effective depth. So 0.48 into effective depth is 125. If after calculating that, we'll get M1 equal to 9.9 10 power 6 Newton into mm. And similarly, we have to calculate what the factored shear force is. Factored shear force is VU equal to W into Lx by 2, that is 11.06 into 3.625 by 2, will get VU equal to 21.07 kilonewtons. Right? After and we have to assume the support width is 300 mm, already given the problem, and we have to bend the main bars into 90 degrees. From that we can calculate anchorage length, and this anchorage length is depends upon angle of bend. So there is a codal provision that for each 45 degrees of bend, there we have to increase we can use the anchorage length is 4 into 5, 4 into diameter. As we are bending it to 90 degrees, so we have 2, 4, 5. So 2 into 45 degrees. So 2 into each 45 degrees, we have 4, 5. 2 into 4, 5 equal to 8, 5. That's why we are using the 8, 5. So 300 by 2, I'm using because I am providing a total width of the support is 300, but bar will be bent to half of the width of the support. That's why I'm making it half. So 300 by 2, that is 85 equal to 150 plus 8 into 8 will get 938. Now check our values. That is 214 will be the L0, and finally we will get total value is 938 mm. Right? LD required is this. According to this formula, if you calculate 0.875 by 4 into tau BD, we will get 376 will be the our LD. And this tau BD value depends upon grade of steel and concrete. Right? Based on the IS 456, we can calculate what is the tau BD is for given grade of steel and concrete. Say if you check that our M1 by VU plus L0 value is greater than LD, so hence we are safe against the deflection. So this is the total reinforcement detailing. Say as we are designing a two-way slab, that is 400, and is that we are using along the shorter direction 8 mm diameter of bars at 180 meter center to center, 180 mm center to center. Along the y direction, longer direction, we are using 8 mm bars, and we are using 220 center to center. So thank you. That's all for today's lecture.